Good morning, everybody. Codeforces round today. It's a Codeforces global round, round 15. So this one is rated for me, so I'm going to be putting my try-hard pants on here. And I'll be doing most of my work on paper, but I'll go over our solutions to all the problems I know how to solve at the end of contest. And you can skip to that if that's what you're looking for. Alright, so we have a string of length n of lowercase English letters of the alphabet. We must choose some number k between 0 and n, and then select k characters of s, and permute them in any way we want. In this process, the position of the other n minus k characters remain unchanged. You have to perform this operation exactly once. Determine the minimum k so that it's possible to sort s alphabetically. So anything that isn't in its sorted spot will need to be moved, and that's the answer. Okay. So we'll read the next word. S equals a.clone, arrays.sort s, and ans equals 0, I equals 0, less than n plus plus. If a at I is not equal to s at I, then ans plus plus is out the ans. Okay, I think this is it, but we'll just submit and then try samples. Looks like we got it. Alright, problem B, running for gold. The Olympic Games have just started, and Federico is eager to watch the marathon race. There are n athletes, numbered 1 to n, competing in the marathon. And all of them have taken part in 5 important marathons, 1 to 5, in the past. For each I and J, Federico remembers that athlete, what is n? Oh, n athletes. So for each athlete and race, this athlete ranked this in marathon J. Federico considers the athlete X's superior to Y if X is ranked better than Y in at least the past 3 marathons. Or in at least 3 marathons. An athlete is likely to get the gold medal if he is superior to all other athletes. Find any athlete who is likely to get the gold medal. There can only be one, right? So you got 10th place, 20th place, 30, 30. So he is not this guy. He wins, loss, wins. So it's the second guy. No, the second beat the first. Win. Loss. Okay, what about the third guy? Lose, win. Oh, there is nobody. Okay. Yeah, we can do this. So there can only be one, but there might not be one. So we just check that. In each of the 5 path marathons, they all have distinct written positions. Okay. So return count is greater than 2. If that's the case, I wins, otherwise J wins. If IK is less than RJK, then plus. Alright, so now we just need to say, for this part, best end equals better at best end I with R, and then Boolean works equals true. If better best end I R is not equal to best end, works equals false. So this out works best end, otherwise -1. -1, 1, -1, 5. Okay. It's good. 1,000 test cases should be fun. Alright, awesome. Whoa, lots of problems. I have problems. Good. Okay, we got it. Nice. On a circle lie 2 endpoints with the following properties. You choose 2 chords that connect 3 disjoint pairs of points. No point strictly inside the circle belongs to all 3 chords. The points are numbered 1, 2, ... in clockwise order. So we have a circle with some points. We choose 3 chords that don't intersect at a point. Oh, any way of choosing 3 chords. No point lies on all 3 chords. Okay. Initially, K chords connect K pairs of points. In such a way that all 2K endpoints of these chords are distinct. You want to draw n minus K additional chords connecting the remaining 2 times n minus K points. Yeah. Each point must be an endpoint of exactly 1 chord. In the end, let x be the total number of intersections among all n chords. Compute the maximum value of x that x can attain if you choose these n minus K chords optimally. First test case, there are 3 ways to draw 2 additional chords, shown below. So we have 2, 8, 7, 3. Oh no, we have 7, 3, and 6, 4. No, we have 5, 1, and 2, 8. Yeah, we have 5, 1, and 2, 8. Gotcha. So you want to like maximize these, I think? Okay. Yeah, that makes sense. So how big is the input? Up to 100. Let's see. So, what do we want to do here? If there's an intersection, it would usually be smart to cross it. What the heck is this? So we have a circle with some things that look like this, maybe. Would you always want to do this? Is it always just connect things that are twice as far away? So let's consider that for a moment. So we have some 4 points. I'm saying you would always prefer to do this over this. Is that true? So if we were to divide, we have to divide the circle across, like separating the red points. Blue doesn't work, but the red also has this advantage here, this advantage here. I wonder if that is the case. Should we just try it? It feels right. I don't have a proof. The hypothesis is we have a circle and we've got some points left over. We have an even number of points left over. The way we connect them is like this, always. I think that is the case. Because like we're for like a thing that goes from over here to over here, what if it goes like this? Yeah, we still get one from this and one from this. We can't get any more. Yeah, so I think this is actually the case. Okay, so this is a fun problem. This is actually a really good problem. This is super unique. I've never seen this before, and it's like its own observation, and it's not hard. Like anybody can make it. So this is a really good problem. Well done to whoever made this. Okay, this is one of my favorite Codeforces problems in a while. I really like it. Okay, so yeah, Although I suspect maybe other people have seen it before, but I think it's really neat because it's so simple. Okay. Anyway, we have N and K. We have all of these, and then we need a Boolean array used. Okay, and now we just need to say int equals 0, and array make equals new int n by 2. So we copy the first ones of these, and then we need unused. So array, or I guess this will be n minus k plus n minus k. Alright, and then int unused n equals 0 for int I equals 0 less than n I plus plus. If not used at I, then unused at unused n plus plus equals I. Unused. And then what else? So now we have our list of unused things, and then for int I equals k, I is less than n I plus plus. Int start, well, int unused int equals I minus k. So int from equals unused at unused int, 2 equals unused at unused int plus unused dot length over 2. Okay, and make at I equals new int array from 2. Okay. Then for I equals 0 less than n I plus plus, and j equals 0, or j equals I plus 1, j is less than n, j plus plus. Int a equals make at I 0, b equals make at I 1. C equals make at j 0, d equals make at j 1. So now we need to see if these things intersect. How does that work? So if A, B, C, D. So we get the min and the max. This one is between them. This isn't. Okay. Static Boolean between int A, int B, int C. Return C is greater than max.min of A and B, and C is less than max.max of A and B. Alright, so if between A, B, C is not equal to between A, B, D, then int equals, or then ants plus plus, and then sys out ants. Should be good there, I think. No. this isn't right. Seven, 1, 1 to 5. Oh yeah, okay, that's true. And then these ones are all half blank for some reason. Why is this? Oh, n minus k times 2. That's right, there are 4 unused things. Okay. So 1 plus 2, and then the next one plus 2. This, we don't need this, we don't need this. Looks good. Alright, took too long, but that's fine. Let's move on to D here, and then we'll listen to CF notifications to see how we do. Pretest pass, this works too. Alright, you're given a sequence of n integers. Does there exist a sequence of n integers b such that the following property holds? For each I, there exist 2, not necessarily distinct integers, j and k, such that AI equals bj minus bk. What? N is up to 10? I'm sorry. Oh, for every. Okay, it's a different array. Gotcha. Okay, so we're given one array. We need to come up with a completely different array such that this is the case. The answer can be no. Can the answer be no? Interesting. Okay. So, yeah, this one is not that bad. When we have something like this first one, we'll use, if it's 0, what if it's 0? Okay, let's say, yeah, if it's 0, let's say it's not 0. Then we need 2 different indices, but these are like half filled. So we know like the pairwise difference between A and B. But we can increase or decrease both of them by some amount. And then for our second index, we can increase or decrease these two by some amount. So let's look at an example in the samples maybe. Can we get a small example? Well, 1, 0 is kind of small. -3, 2, 10, 2. So we'll start with these two. We'll just take 0. Okay, we'll take question mark and then question mark -3. Okay, so we've satisfied the first one. And then we'll have this one will be question mark +2. This will be question mark +2 as well. So we've got this duplicate here. So if you have a duplicate, that works. Okay. So then we happen to... Oh, so then this needs to be question mark +10. Yeah. And then this one happens to just be solved by chance. So we can solve all but one easily. The question is, how do we get the free one? So when is that the case? If we have like a duplicate, if we ever have a 0, -4 -7 . Well, okay, it doesn't matter what the first element is, because everything is a difference between two elements. So the first element in the array, we'll just make it 0. Okay. So is the difference between any two elements in this array equal to something else? 1 minus 4 is equal to 5, or 4 minus -1 is equal to 5. Two minus 2 is equal to 0. Why is this true? Well, it's not, okay, so I'm basing everything off of, like, I'm only checking a very small subset of the arrays. I'm checking these pairs. But like n is only 10, and we know the first number is 0. So, like, how many choices are there? For this, you have 0. For this, seems easy to fail system tests on if you don't have the right answer. For each I, there are 2 indices that are pairwise. Okay. I'm looking for indices so I'm going to choose some numbers. Yeah, do you always want to base it off stuff before you? Maybe. Maybe it doesn't matter. Oh, so you can go 0, like -3 plus 2, like -3 plus 2 or whatever. You can go plus or minus 2. Yeah. So 0, plus or minus 3, plus or minus 2, plus or minus whatever. And then you want to see, can you hit something else by chance? Okay, so we need 9 factorial. Yeah, we do the 9 factorial and then we're good. Okay, so in this case, yeah. Okay. So we'll get all perms, and then 4 into place equals 0, to place less than perm.length, to place plus plus. So considering placing this, if used at to place, then continue. Otherwise, used at to place equals true. And then we'll place the thing, and then we'll unplace it. And then here we'll say perm at end equals to place. And then all perms of the same permutation, same used, one more index. And this will give us all permutations. Okay, so then we've got all permutations. This is much easier in C++, but that's fine. Okay, now what? So int n equals this. Perms.clear, perms equals all perms of new int array n, new boolean array n, and then index 0. Oh, I guess just by this. Okay. So now we have all permutations. Wait, we really just want any subset of pluses and minuses, right? Yeah, that's what we're looking for. So we don't even need this permutation nonsense. Ooh, this might be a bit big. Our runtime's going to be a bit uncomfortable. I guess maybe we can optimize it to bit sets if we need. So reachable equals this. Okay, then we need to swap these. So temp equals reachable, reachable equals next, next equals temp. And then sysout works yes, otherwise no. So our runtime here is 2e8, but this is the slow part. This is literally all logic, so I think we should be fine here. Next at J, I mean. Reachable at I, or I plus J is less than max, or J minus I is greater than or equal to 0. Minus 7. Oh, we might as well just make all of these positive, right? Don't think it matters. Yeah. What? Why not? These two add up to 5. Oh. Yeah, this is wrong. TLE. Oh no. Oh, looks like we got it. Okay, nice. Oh my goodness. Oh, bro, if I fail system tests, I'm gonna be upset. Okay. Colors and intervals. There are n numbers. 1 to n times k are colored with n colors. The colors are indexed 1 to n. For each I, there are exactly k numbers with color I. Let me try that again. The numbers 1 to n times k are colored with n colors. These colors are indexed 1 to n. For each of these colors, there are k numbers with this color. Wait. Yes. Okay. N numbers, k copies, or n colors, k copies of each color. Okay. Let a comma b denote the interval of integers between a and b, inclusive. So we have a set of intervals. Okay. We want to choose n of these ranges such that for each I, it holds that ai is less than or equal to bi is less than or equal to n minus k. So we pick a bunch of ranges of numbers between 1 and n times k. For each I, the numbers AI and BI are colored with color I. Okay. Each number belongs to, at most, this many intervals. One can show that a family of intervals always exists under the given constraints. Okay, so let's try this one more time. We have this thing. We have some array of numbers up to n. They're numbers up to 4. We have 3 copies of each number. We want to pick n different ranges. So we want to pick one pair, or we want to pick, one pair? Can AI and BI be the same? No, AI and BI have to be different. Okay, that's where I was confused. So we need to pick a bunch of non-empty ranges, and each element can be a part of at most n over k minus 1 ceiling. Okay. Square root of n is only 10. Tourist is actually on fire. What a legend. Solving problem. It took him 6 minutes. What the heck? What the heck? What a genius. Six minutes to solve problem I. Six minutes, bro. 6 minutes. Probably took me 6 minutes to solve. I'm sure it's taken me 6 minutes to solve problem A before. Oh boy. All right. This is a difficult to wrap your head around constraint. Like we don't want that many overlaps here, is what we're looking for, I guess. Suppose we choose the closest pair each time. Yeah, that's an interesting play. How close is the closest pair going to be? So we have numbers numbers 1 to n, and then we have k copies. So they need to be spaced out every n, right? This is every n. So this seems like it wouldn't work because we could get this by accident. Now we have 5 intersections, but we're allowed 5 over 3 ceilings, or 5 over 2 ceilings, which is equal to 5 over 2 is 2.5, so it's 3. We're allowed 3, but we've used too many. Yeah. Well, if we use the closest pair, that's kind of helpful. Yeah, if we use the closest pair, we know anything we do in the future will overlap this pair. Yeah. So let's say we find some arbitrary closest pair. Then we have problems though. Like if we choose this pair, then it's also like not necessarily true, I don't think. Because the distance decreases when we remove the ones from other stuff. It's like some other pair might decrease by 2 or more to become even better than us after we're played. Okay. So n's at most 100. K can be up to 100. So what if n is almost k? So if n comma k, well yeah, if k is big, then it's hard, right? Why is it hard if k is big? If k is big, we're allowed a few groups, but like k is small, then if there are a lot of copies, it's easy to do. Maybe it's just like some greedy. It feels like there's a way of doing this greedily. We can like keep track of all of the sets, right? So we make this decision. Yeah, first of all, there's no reason to, yeah, we would never make this, because like this is just strictly worse than one of these two. Okay. So you have these candidates. So this one is affected by this, like some continuous, a bunch of them. What if we just matched randomly? I guess that's probably unlikely we would get it right. Is it? So it's tricky. Got a brand new box of Cliff Bars. Hope someday Cliff sponsors me. How amazing would that be? I love Cliff Bars. They're literally such an amazing food. You can like live entirely off Cliff Bars, and it's easy, no worries. They're like moderately healthy. I don't know, maybe they're not healthy, but they taste good. we've had our break. Let's read F. It seems unusually easy for its position. Oh, it's also the same difficulty as E. So there's that. All right. An ant moves on the real line with a constant speed of 1 unit per second. It starts at 0 and always moves to the right, so its position increases by 1 each second. There are n portals, the ith of which is located at position x, which teleports to position y, less than x. Each portal can be either active or inactive. The initial state is determined by SI. So they start either active or inactive. If the portal is inactive and it becomes active, when an ant travels through a portal, if the portal is inactive, it becomes active. If the portal is active, it becomes inactive, and the ant is instantly teleported backwards, where it keeps working, or keeps moving as normal. For how long, from the instant it starts moving, does it take for the ant to reach position xn plus 1? It can be shown this happens in a finite amount of time. Are each of these distinct? Yes, everything is distinct. So it's at position 3, goes back to 2, and then why is there a 0 here? It starts off. Okay, a picture would be nice, but it's all right. How big is this? This is, or wait, what are they asking? xn plus 1, okay. So position, so we start, where does it start? Position 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 3 to 2, starts off. Then we have 6 to 5, starts on. Then we have 7 to 4, starts off. Then we have 8 to 1, starts on. Okay, so we're walking. So this is, we do this part once. Now we do this part twice. So we're going to do it twice. What does that mean about this next step? How many times do we do this next step? Well, the first time we do it, it'll be off. So we just walk through once. But the second time we do it, it'll be on. So then we do this 3 times. Okay. But then we do this twice. Okay. So we're doing this twice. So now this thing happens 3 times the same way, same reason, right? And this also happens 3 times. And then this part happens twice. This part happens once. So this happens 3 times. So we walk into this 3 times. So that once, over, so 3. So we have like it's on 1. Then it's on 0, then it's on 1. So this is 5. Okay. Was it that easy? Was walking through the first sample enough to solve this problem? Is it that easy? Okay, 1 plus 2 plus 3 plus 2 plus 3 plus 5 plus 3 plus 2 plus 1. 22. Am I off by 1? Why 22, not 23? So this happens once. Yeah, I guess let's just draw this out. So we have, they say 1 to 6, then 5 to 8, and then 1 to 3, and then 2 to 6, five to 7, 4 to 6, 5 to 9. So 1 we check out, 2 we check out, 3 checks out, 2 checks out, 3 checks out, 4, 2, 3, 4, 5, 6. So this is not 5. 3 checks out, 2 checks out, 1 checks out. Okay. So you walk into something once. We're going to walk into it 3 times. So the first time you walk into it, oh wait, if it starts on, what happens if it starts on? Then it turns off, but it turns on again. Gotcha. Yeah. So if it's like 3 on, then you just change it to 6. 3 off changes to 5. No, changes to, what does 3 off change to? Yeah, to 5. So 3 times 2 minus 1. Okay. Easy mode. EF. Don't know how to do E, but this problem should be easy. Okay, so static class event implements comparable int x boolean on boolean start event earlier public event so sort them just by x's, which should be easy. This is int x boolean on boolean start. Dot x equals x, this dot on equals on, this dot start equals start. I guess we'll just pass in the earlier two. I was considering making a second constructor, but I can just be smart later on rather than being smart now. How about that? Okay. Good. So a single test case. Event array events. There's a new event array 2 times n. 4 equals 0, less than n, plus plus. And start equals this, end equals this. Boolean on equals fs dot next dot equals 1. Okay. So event start event equals new event. So it's start. Boolean on will be yeah, this does matter. So this is on. Start is true. And then this is null. Event end. Okay, I guess we just don't need the start part. It's redundant. Yeah, okay. End event equals new event. So this is the end. On, we don't care. I guess I'll just set it to on. Earlier is start event. Events at 2 times I equals start event. Events at 2 times I plus 1 equals end event. Arrays.sort events. Int times equals 0. Long ants equals 0. I guess equals 1. And then sysout ants times equals 1. Int x equals, what does the x equal? 0. Int count before. For event e and events. E dot count before equals times. Oh, this has got to be a long. We don't need our mod. So, gotcha. Okay, so we have this. This is count before is a long. Good. Okay, so we have this event. If e dot earlier is null, this is a start. Otherwise, this is an end. Okay, so now we need to int dx will be e dot x minus x. X equals e dot x. Ants plus equals dx times, or multiply. Add ants to multiply dx by how many times we do this part. Then what now? So x, we do, okay, so now we have to process this. So if this is the end, then times equals e dot, oh wait, that is not true. Do they guarantee none of these overlap? Why is this one so weird? Oh, I guess because it's under mod. Yeah, so let's think about this, actually. I might not have the answer. It might not be that easy. Okay, so we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 2 to 1. This is on. 6 to 4 is off. 8 to 3 is off. Nine to 7 is on. Then 10 to 5 is off. So what does this actually look like? So this part we do once. This part we're going to do twice. We came here twice. So this is once, okay. Because we divide by 2. Is it times divided by 2? So if it was on, yeah, then divide by 2. What if it was off? Then you do plus 1 divided by 2? Maybe? Okay. So here, we're going through this part once. It's only going to happen once. Yes, this is just once, right? Oh, it's not... We can't make that decision. We don't know how many times we're going to be here. Like, it's kind of once, but it's also not. Because it's going to be here once. So this is like, yeah, so this thing has an arrow to this. Like, we'll get here, then we'll go back to this. Then we'll get here, and then we'll go back to this. So really, this is happening twice. Yeah, that's tricky. If a portal's initially on, if there's nothing in between it, we can just treat it as being on forever. Yeah, I guess the question is just how many times does for each portal do we cross it? That's the important part. Yeah, because it's just the distance to the end plus the portal length times the number of times you cross it. So what does this look like? We know this part happens once. What about this part? Well, we only get here, we're only leaving this once. How many times do we need to get here? Probably just once. Okay. If we leave this thing once, that means we need to enter it twice, right? Yeah. So, yeah, you have to enter it twice. Okay. So you're in this twice. If you leave this thing twice, how many times do you have to enter it? To leave something twice. How many times do you have to enter something that's off to leave it twice? You have to enter it 3 times. Is that true? So you enter it 0, then you enter it again, or you enter it and this counts. You enter it again 0, then you enter it again 1. Oh, so 5. Then you enter it again. So this counts, doesn't count, counts us. This is 3. So 2 times 2 plus 1, or minus 1. So this is 3. Excuse me. What is this? So we're here 3 times. We were redirected twice, so this is a 1. Is that the case? Yeah, so we were redirected once. This happened once, which means this should be a 2. That sounds plausible enough, I think, right? Yeah, probably. Okay. Oh, so we can mark all of these things when we see them. So this happened once, this happened. Yeah, okay. I think this is the right solution. Yeah, so you just, I'm kind of right, you just have to go backwards. Okay, so what do we need to go backwards? So we need the previous event, we need the number of times it's used. So we'll store all the end events and then all of the events. Sounds good. Then, what do we need to do here? So this should just be the last end event. So for the last end events, x plus 1, that's our answer. We print the answer at the end. Then we just, here we need to say how many times is each event used. So for events E and end events, ans plus equal, or ans equals add, ans to multiply e dot times edges used by e dot x minus e dot's earlier dot x. Yeah. Cool, and return answer. So I guess we can just sort these in reverse order. Or x compared to x. We don't need to know the x. We do need to know how many times we're there. Yeah, okay. So initially it's just once. So let's process the end first because it happens first. So what do we need to do here? If an event ends, it depends on whether it's on or off. So if it's on, what does this mean? We need to know the new number of times. So long times taken will be, if we need to exit, or times the edge is taken. So if we need to exit it 3 times, that means we need to take the edge back 3 times. So this is just times. Yeah. Okay. And then in the future, times will be times by times. E dot times edge used equals E dot earlier dot times edge used equals times edge is taken. Okay, what if it's off? So then long times edge taken will be times minus 1 times equals add times edge taken. E dot times edge used equals E dot earlier dot times edge used equals times edge is taken. Well, let me clean this up a bit here. Okay. What if it's a start event? So now, yeah, we have a start event. So in this case, times minus, or times equals sub. Times minus e dot times edge used. Minus 35, what? What? I have the other one. Where is it? Here we go. Okay. Event ending at 2. There's an event ending at 2. What? Why did they do this? Okay. $21 is not the right answer. Event ending at 3 was hit 1 times. Was it hit once? You go through. Yeah, okay, so this is once. Event ending at 6 was hit 3 times. Yeah, it's true. Event ending at 7 was hit once. Yeah, okay. Event ending at 8 was hit once. So it's 9 plus 7 plus 1, 2, 3 plus 1 times 3 plus 1, right? It's 23. What? Oh, this is end events. Okay. Looking good. Okay, not great at all. Yeah, not great at all. But we can try and get E, and that should help. Lots of people are able to get E, so it shouldn't be that bad. Okay, so we need some way to construct an answer here. Yeah, so as soon as you're like, hey, let's go backwards, then it's not too bad. But the question is just how do you do it for E? F wasn't too bad, I mean, when you decide to go backwards. Alright, I'm gonna go to the bathroom. So we can make an equivalent problem. We have a bunch of nodes. Each node has an edge to some other node. We have a bunch of colored nodes. Yes, we have a bunch of colored nodes. Each node has an edge to some other nodes. We need to pick one node of each color. And what else? Yeah, it's tricky. So if there are any things next to each other, we take them. Yeah. And then we can remove all whites. So this is like n over k minus 1 ceilinged is what we're doing here. N minus 1 over k minus 1 ceilinged. So on average, you cover about this many nodes with a crossing. So there's this many total, and it's split up into k parts. If we just take the first one that ends, what happens? Yeah, can we just be greedy? Just like take it if we can? We probably should, right? So when we see, okay, we've seen this one before. If we can take it, we take it. So now we've removed all ones. Can this ever be a bad decision? I have no proof that this works. Why would this work? Okay, so I don't know how to break it, but also, yeah, I don't know that it would work. Like, for the first thing, is it true? Probably. We have a 1 we could take. We might as well take the 1 because it's going to hurt us the least, and then we get rid of all 1s in the future. I do not have a proof. I don't have a proof. It seems possible that it's just do it. Like, we have a 1, 2, 3, 1, 2, 3, I guess. So then we do this. So now we have an overlap of 3, which is fine. I don't know. What do we need for this? Seg tree with range add and range max. I can code it up. Shouldn't be hard. L child new seg tree, new st from leftmost to mid, r child new st from mid plus 1 to rightmost. Okay, and then we have void recalc. If leftmost not equal to rightmost, then okay, we need void max, return max plus prop. Int max. What is this? So this is if these are equal, then return. Otherwise, max equals math.max if max or lchild.max, and then rchild.max. Okay, then we have void prop. What do we do for this? So we recalc after, and then we say lchild.max plus or lchild.prop. Okay, if leftmost not equal to rightmost, lchild.prop plus equals to prop, rchild.prop plus equals to prop. Prop is equal to 0. You can probably just update max by it, to be honest. We'll recalc. Okay, so then we have void range add int L, R, and D. L is greater than rightmost, or R is less than leftmost. Then return. If L is less than or equal to leftmost, R is greater than or equal to rightmost. And to prop plus equals D, return, otherwise propagate. Recalc at the end, and then lchild.range add this, rchild.range add this. Okay, and then we have int max from int L to int R. If greater than or equal to this, then we return integer.minValue. If it covers us, then we return max. Otherwise prop. Recalc, I guess at the end. We probably don't need to. Do we need to? We don't need to. Then we do return math.max of lchild.max from L to R, or rchild.max from L to R. There, segment tree. This is single test case. Okay. This seems very wrong. My runtime is too fast. Okay, bro. Maybe they'll break it? So what is this? So this is going to be from 0 to n times k. Okay, so then int array last equals new int array n. Alright, so arrays.fill last minus 1, for n dot equals 0, less than a.length, plus plus. If used at 8i, then continue. We've handled this color. If we haven't, okay, so then we have to say if last at a at I is equal to minus 1, and last at a at I is equal to I, and then continue. Otherwise, we need to consider range. Consider this range. So int max thickness will be n over n copies minus 1, n plus n copies minus 2 over this. So if n is 2, or if k is 2, it's n over k minus 1. Yeah, so that's fine. Okay, so if st dot range or dot max from range start to range end is less than max thickness, then place it. Right? Let's try it. St dot range add from range start to range end. Place a thickness of 1. Okay, then used at a at I goes true. Cool. And then answers at a at I equals new int array from, what is the start? Where do we start? We start at range start and at range end. All right. One, two, three, four, 5, 6. We should have done this. We should have taken 1 to 5. Why did we not? Write a segment tree. It is 1. What's wrong with that? Oh, gotcha. Okay. So the 1s were taken from 4 to 5. The 2s were taken from 7 to 9. 4, 5, 6, 7, 8, 9. And then we took these 4s and then these 3s. To 11 seems fine. Please have good test data. Please have good test data. Wrong? Oh boy. How many pre-tests? Oh boy. I have no reason to believe that's right. Oh. It is a sketchy contest. Both of these things could just be totally wrong. Ugh. Okay, let's see if we can get G. I don't know why it's right. So many things. It just feels right, you know? It... We're just stressing out over here over this. Like, okay, we have 45 minutes. Let's get G. Andrea has come up with what? He? Okay. He believes to be a novel sorting algorithm of length n. The algorithm works as follows. Initially, there is an array of n integers. Then k steps are executed. For each one is less than I is less than k. During the ith step, the subsequent array, the subsequence of the array A, with indices j, I1, I2, iqi, is sorted without changing the values in the remaining indices. So you sort some things. Is to a solve set yet? Bro, this is an embarrassment. You just speed ran the thing. Oh, yikes. This is hilarious. This is just like comical. It's actually just funny that anyway. During the for each I during the ith step, the subsequence of the array with indices this is sorted. So you sort a prefix. Andrea, being eager to share his discovery with the academic community, sent a short paper describing his algorithm to the journal, Some Sort of Sorting Algorithms. You're the referee of the paper. That is the person who must judge the correctness. You must decide whether the algorithm is correct. That is, if it sorts an array A, if it sorts any array of n integers. Oh, so you... Wait, what is J? So there are at most 10 steps. And the number of steps. So there are most 10 steps going on here. N is up to 40. There's an array of 40 integers. Then you do up to 10 steps. For each thing, during the ith step, the subsequence of the array is sorted. So the ith step, we pick some integers and sort them. Yeah. Got it. Yes, okay. It's like we sort 1 to 2 to 3, we sort 2 to 3 to 4, we sort 1 to 2. So accepted. Dominator trees! Okay. 1, 2, 3, 4. We sort 1 to 2 to 3, right? Is that what we said? We sort 1, 2, and 3. Then we sort 2, 3, and 4. Oh, but this, so it's not actually dominator trees because this can get moved here. Then we need to sort these two. So this is true. Okay. Sort 1 to 2 to 3, sort 2, 3, and 4. Sort 1, 3, and 4. Yeah, but 4 could be the smallest. We should read I. You're organizing the famous Zurich Music Festival. There will be N singers who perform at the festival, identified by the integers 1 to N. You must choose in which order they're going to perform at the stage. You have M friends, and each of them has a set of favorite singers. More precisely, for each I up to M, the ith friend likes some set. Okay. A friend of yours is happy if the singers he likes perform consecutively. Count the number of valid orderings. is 100 factorial. This is 5 factorial. This is 2 factorial. Some other stuff. Is this actually just really easy? We need to know the number of things in each group and the number of groups, right? Like the groups can be in, ooh, not quite any order, almost any order. You might have like one group inside of another group, sort of. Yeah, I don't know that that's my best problem for me to solve. What's my minus 25? Not the worst. Could be worse. Okay, let's get G. Or I guess let's just check the problems first. Yeah, probably G. Probably. Oh, maybe not though. Guess the perimeter sounds like, let's call a point on the plane admissible if its coordinates are positive integers less than 200. There's an invisible rectangle such that its vertices are all admissible. Its sides are parallel to the coordinates axis. Oh my goodness. We want to guess the perimeter of the rectangle. We can ask at most 4 queries. We need to know its perimeter. Ooh. So we just have to guess the perimeter. you do get a lot of information back every query. So you can get the area of the rectangle in one query. Yeah, you can get the area in one query. That's neat. We'll say you know the area. If you know the area and the height, this tells you the width. So we ask that, and then this, and we get these points. It's an axis. Wait, is this not easy? Okay. Its vertices are all divisible. Its sides are strictly parallel. The area is strictly positive. We want to guess the perimeter of this rectangle. Choose a non-empty subset. Count how many points are in the boundary. So if we do this, if they're the same, what if they're the same? Then we have this. Now we have a problem. So yeah, so that's the issue. So if they're the same, then what if we do every 3? Yes, I am asking for too much information. I'm asking for the area and the height. I don't need both. I need the area. Well, I don't even need the area. I need the height and the width. If I can get the area, that's a good combination, but I don't even need the height and the width. I need the height plus the width. So that would look like this. Yeah, what if I do this? They would make it even like this. Then this one would have 5. Oh, so if this is even, if it's even in both height and it's a rectangle, not a square. If it's even in both dimensions, then this doesn't help because these are the same. Yeah, it could be like 2 by 4. What if it's odd? We want to like be able to differentiate even from odd dimensions. Here. Okay, so is this array always sorted if we sort these indices at these times? Could we do like a DP, like could this inversion exist at this step? It's a bit tricky, I think. Could this item be here at this step? Could this be a 4? Yeah, well, let's say we've got a permutation. 0, 1, 2, 3, 4. If 4 starts in this position, does it have to end here? I mean, there are a lot of choices. So like if we were to sort these ones, what happens? That tells us like where we go is kind of dependent. And we've used these, like these are fixed. Assume everything else will get into place other than the 4. So we just want to see, can the 4 end up in the wrong spot? So there's nothing after it, so it needs to be, well, okay, 4 is a bad example. Maybe we pick a 2 instead. This is a 2, so now it's here. So we've used one thing. So this is like DP. So excuse me, like dp at your position in the array. I guess your value matters. The step you're on matters. It's messy though, like which things are after you can be screwy, like so we have 1, 2, 3, 2, 3, 4, and 2, 4. This sorts it for sure. Why is that? Or 1, 2. So what possible, after these two things, like what are the possible inversions? So 1, 2, 1, 3. Why can 1, 4 not exist? So we pick these 3, and then these 3, and then these 2. So I guess what are the possible inversions at this step? Everything is possible. Then after we sort these 3, we don't have this inversion anymore. We don't have this inversion. We don't have this inversion. But each of these 3 inversions are still possible. So if you sort a group, it removes all inversions within the group. Yeah. So then when you sort these 3, it removes this inversion and this inversion. But you still have this possible inversion. And then wait, so that means like which positions can this be in also matters, because it's now in the front. Or is it? So this needs to be, it's in front of this. Or it comes after this. So it has to be smaller. I don't see it. I don't see it. So something less than you before you, and something bigger than you after. If something is less than you and before you, it's never going to come after you. Yeah. Yeah. Yeah, so let's just focus on us. So we know, like, if a query doesn't involve us, we can skip it. I guess this is good to keep. So let's say we don't have this. So we have 4 positions. We're interested in the 3. So when we have 1, 2, 3, let's say we start here. Okay, so yeah, we have this. So I guess what is the transition? So like if it doesn't involve us, we don't care. If it does involve us, we need to know, like, we also need to know like the number less than that we've used. Well, that's not true. We can move ahead of someone. Yeah, so you could have like a 3 get put here, a 3 and a 1. And then you can have a 4 here and a 3 here and then a 2 here. So initially you've got these two sorted, and then you can sort these two, and then you have the 3 in front of the 1. I guess maybe we should just look at, could the 1 be out of order? Does the smallest thing have to get to the first position? Yeah, if the smallest thing has to end up at the first position, we could delete it. Maybe? Possibly. Let's go with that, because we're low in time. And this contest has been a lot of guesses, a lot of unproven guesses. Does the first thing have to get to the first position? Well, every position needs to eventually be compared with the first position. Yeah. Once the first thing is in the first position, it'll get there and stay there forever. It'll always move up to the earliest in this group, though. So if the first thing, yeah, so what is the first thing? Brute force. And then does it get to the first position? How much time do I have? There's no way. We have to remove it. Yeah, so how do we how do we ignore the first position in future queries? Now we know the inversion doesn't involve the first element. As it's not really an inversion that matters. It's just something winds up in the wrong spot. If it's 2 away, I guess there's still kind of 2 inversions. Okay, anyway. What about the second element? So how do we look at the second element now? Seeing if the first thing winds up in the first spot is easy, because you can just simulate it from every position. What about the second thing in the second spot? Depends what the first thing is. Like, where you go matters. And then we can't do a 40 choose 20 thing, because that's going to be way too big. Yeah, I'm not getting anywhere here. Honestly, with a 30-point rating dip, I'd be fine. Yeah. It looks like I'm probably going to keep IGM unless I fail system test, which is entirely possible. Maybe we shouldn't be spending this time trying G. We should be spending it... G also has so many wrong submits. Oh my goodness, look at that. Yikes. Yep, I'd like a proof of this. The proof is in the pudding. Or I guess it's not. The solution's in the proof. How about that? How do you prove that this is sorted? You can try everything, but that is not how they verify. I don't know how to do it. I don't even know where to start. The problem with small bounds is it just like you have so many possibilities. Oftentimes I feel like even like harder problems, you can make a hard problem, or you can make an easier problem harder by making the bounds small. You can trick people who are otherwise good by like convincing them that there isn't an easy solution and they have to do something complicated when that's not the case. really want to know what the solution to H is. Honestly, these are all very good problems. I mean, maybe I is too easy or something? It's kind of funny. There are I problems in a Codeforces round, which usually has 5 problems, so it has 9 problems rather than 5. And then it's still too easy for a tourist, anyway. But I don't know. This seems like a fine scoreboard to me. Interestingly, there are no hacks. So maybe my solutions are fine. It seems like a really terrific set, honestly. Yeah. GHI, I don't have solutions to. But that's fine because like I think my rating is slightly higher than it should be at the moment. I think it's maybe a bit generous. So getting knocked down a peg is fine. Plus I get to be next to Monaghan and Isis FFT, you know, so I'm happy. Nice job for Ixian though. Nice job. Congrats on the IGM. Also, I'm solving as many problems as Andrew He. What? Yeah, this is brutal. You see that tourist gets it, and then it's like, tourist got it in 6 minutes, I can do it in an hour, and then you just like, can't. Yikes. Yeah, I don't know, maybe I'll think about like C for a moment here. Well, C I'm pretty confident in. C is less of a sketchy thing. E is the real question, like, why does this work? Why is this answer right? I'm saying that when you see a range, you should take it if you can, going from left to right. Well, for one color, it obviously works. Because, like, yeah, we'll take as many as we can of this color. When you start having 2 colors, then the logic is something like, I can take this, and then that's fine. Or I could use this in the future, but like, yeah, it's not necessary. Because all of this space is unhelpful. For some color. It's really more of a hot read on the proof than anything. Okay. Well, let's talk about solutions anyway. I think we'll do that, and then we can see if we fail system tests. How about that? I don't have G. I have A through F solutions. All right, problem A. So subsequence permutation. So what's going to happen is you're going to choose some elements of this array. You're going to sort them and keep everything else in the positions that it was before. So in the example for Andrea, they picked the A, the D, the E, and the A. They pick some way of permuting them, and then it becomes something else. Now, obviously, since you want to sort it alphabetically, you're going to sort the permutation. And yeah, there you go. So here's the question. What things are mismatched? So if you have, was Andrea the name? Andrea. Okay, if you sort this alphabetically, I think you get A, D, N, R. Think. So what things mismatch? Well, this is okay. That's good. These don't match. These do match. I'm missing an E. Okay. These are in the same positions, but they don't match. These don't match, and these don't match. Obviously, if these things match, you can like ignore them. But for everything else, that means it needs to go to some position where it's not. So this needs to go here, this E needs to go here, the R needs to go here, and the A needs to go here. So since these 4 things all need to get moved, they need to get swapped with each other. So what you can do is pick these 4 things and then move them around. So the answer to problem A is just how many things don't match their position in the sorted array, which is really easy to implement. You have your array, you make a copy of it, sort the copy, and then check how many mismatches you have. And that is the solution. That easy. So the full screen with that. Cool. Yeah, that's problem A. Pretty straightforward, I think. For problem B, you have a marathon race, and then you have this different type of voting. It's like, well, I don't know. Maybe it's not voting. You have a marathon. The flavor text they give in the problem is you have a marathon race, and then there are 5 events, 5 marathons in the past, and you're better than someone else if you beat them in 3 or more of the 5 marathons. Obviously, if A is better than B, B can't be better than A, right? 2 people can't both be better than each other, because if you beat someone in 3, then that means they lose in 3, so they can only beat you in at most 2. So if there is some answer, it's unique. It's possible there isn't a unique answer, or there isn't any answer. There isn't any person that beats everybody else. But if one person does beat everyone else, then no one beats him. So you can keep track of some candidate answer, and then walk through the entire array, and then make like your new candidate answer be the winner of these 2. And eventually, what'll happen is you get to the end of the array, and you'll have some candidate answer. So now you know either this person is the answer, or no one is. And when you have that, you just check that person against every other person, and if they beat all of them, they're the answer, otherwise nobody is. So that's pretty easy. What I did for that is I have this array, so this is each first array, or each first index is like the person, and the second index is which marathon. And then I have this helper method, which counts if you compare I to J, and how many times does I win, and which one of these 2 is better. So first I count how many times is I in a better place. Does I place before J in the race, so I beat J. And then if I is better, return I, otherwise return J. And you're guaranteed there are no ties, so this works just fine. So yeah, so we walk through the array, we keep track of whoever's the best, and at the end we verify it. If this person ever loses to someone, we set works to false, and then print that at the end. Okay, that's problem B. For problem C, this is completely different. What is this? Oh yeah, we have the circle with some chords. So yeah, so we're given a circle, and the circle has some lines in it already. Maybe it's got like this line, and then it's got this line here, and then it's also got some points on it that you get to put your chords on. So maybe these points are like these 4 points, for instance. And you're gonna draw, there are 4 blue points, so you're gonna draw 2 lines. And these lines, I mean, in this case, there are 2 ways of doing it. You can do it like this, or you can do it like this. And you wanna do it in such a way that you maximize, actually you could also do it like this. So there are 3 ways. You wanna maximize the number of intersections between any pair of lines. So if you were to do it like this, there would be 1, 2, 3 total intersections. A better way of doing it is to do it like this. In this case, you have 1, 2, 3, 4 intersections total. They also say, like, don't worry about if 3 points or if 3 lines intersect at a point. Just treat it as like this, because you still have 3 pairs of intersections. And it gets kind of weird if like they all intersect at a point, but they're just like, don't worry about it, right? Make the lines like a little flimsy, move the points around a bit so it doesn't happen. So yeah, that's part of the problem too. Okay, so we've got that. So what's the observation here? It turns out, let's consider the problem without any red lines for the moment. So let's say I just gave you a circle with some blue points. Like this. Maybe we'll draw 6. So what's the best way of doing this? Well, I don't really have a formal proof for it, but it should be somewhat clear that you want to connect each point with the farthest away point. So now each line will intersect every other line. And you have n choose 2 intersections, which is the most you can possibly have. So let's say we do this. Now we're going to draw some red lines here, and these are the ones that we're given. And maybe we're given this line here, and we're given, oh, I don't know, maybe we're given this line here. So let's draw it like this. So this red-red intersection, we can't choose that, but everything else we can choose. And here's the proof, which I've just discovered right now. So the blue intersections we've maximized. We have every blue line intersecting with every other blue line. The red-to-red intersections, those are given to us in the problem. We can't choose them. So now the only thing we might want to do is we might want to remove some of these yellow intersection points for some blue to red intersection points. If we can remove one yellow and get multiple blue-red intersection, right? So it's possible, hypothetically, it might be possible, that we can do better than this by improving our red-red intersections. But it turns out that's not going to be the case. And here's why. It turns out we have the highest possible number of blue-red intersections as well. The reason for that is, let's look at some red line. So in this case, we've got this red line here. How many intersections could this red line have? It's got 2 blue points on the left and 4 on the right. At best, it can have the minimum of these 2. It can't have more than 2 intersections with a blue line. Because in order to get an intersection point, you need to pair up one thing on one side with one thing on the other. So at the best, you would use one of these each time, and then one of these again, and now you're out of things on this side. And that's what this algorithm will do. So if we pair stuff up like that, we'll get that optimal number. Okay, cool. So that's how you do it. In order to actually just count, you just make this pairing, and then you can just naively do the pairing yourself, and just see, do these things intersect. I guess to implement that, I'll show you the code real quick. It's not too bad. So we have all of the pairs that were given, and then we have whether each point is used. We read in each of the pairs and mark them as used. And then I have, these are all of the unused elements. I read them into this array. And then these are all of the pairs that are made. So there are n over 2 of them. And then this is like L to R, right? These would just be like pairs in C++. So the first k are the ones we're given an input, and the rest of them, we just take each thing. So here there are 6, so we take this first one, and then we go 3 over, and we match it with this one. Then we take this one, and then we go 3 over, and we match it with this one. So these are the first 3, they match with the thing 3 after it. And then finally, we just count to see, do these things actually intersect? And this is the logic for that. So just check, is C between A and B, between like the minimum of A and B and the maximum of A and B, and is D between A and B? And if these two are different, that means lacrosse. Cool. So yeah, that's the idea for C. Awesome. Let's talk about D here. We have a sequence of n integers. Is there a sequence of these? Yeah, okay. So here's the thing for D. So let's say we only want to satisfy all but one of the things in the array A. So I guess let's talk about the problem a bit more. Yeah, okay, so yeah, finish C, done at C, on to D. For D, so the problem is you've got some array. Let's use the array they give us. 4 minus 7 1, or minus 1, sorry, 5, 10. Okay, so we want to come up with some new array. Maybe the array looks like 0, 4, 7, 1, 5, hypothetically. And we want, for each number in this original array, we want there to be a pair of numbers, I and j, where if you take one element minus the other element in this array, then you'll get the element in the first array. So in this case, it's possible with the first two. You can do this minus this, and that'll give you 4. If you want 7, you can do 7 minus 0, that'll give you 7. If you want minus 1, sorry, if you want minus 7, you do 0 minus 7. If you want minus 1, you can do 0 minus 1, if you minus 1. If you want 5, you can do 0 minus 5, and that'll give you 5. But you can't do 10. There are no two elements in here that'll sum to 10. So 10 isn't possible. So this, what that means is this array here is not a solution to B. But there is some solution to B, we just haven't found it. Okay, so a couple observations here. First, things being negative is not relevant, right? We can just make them positive. And the reason for that is if we satisfy the fact that there's a negative 7 here, right? So let's say we satisfy negative 7 by 0 minus 7 is equal to minus 7. We also satisfy 7, right? If you flip these two, then you have 7 minus 0 is equal to 7. So satisfying the constraint for negative 7 and for 7 are the same thing, which means we can just make all of the numbers equal to their absolute value, and now everything's positive. Okay, so that cleans things up a little bit. It doesn't really matter too much. Here's the next thing to notice. What we're doing here is we're building a very constrained version of the array. In this case, it's everything minus the first element for our candidate idea here. But this is not like required. We didn't have to make it everything minus the first element. We could have done everything minus the element before, for instance. So if we make the cumulative sum version of this array, we could have something like 0, 4, 4 plus 7 is 11, 11 or 7 plus 1 is 8, 1 plus 5, or sorry, okay, try again. 4 plus 7 is 11, 11 plus 1 is 12, 12 plus 5 is 17, and then here's this array. So this array, again, we haven't satisfied 10. There are no pair that differentiate to 10, but for everything else, it works really nicely, right? So we can do the subtraction of adjacent elements, and that'll give us elements 4 through 7. And the difference is for this array, the pairs look like this. For this array, the pairs look like this. But we can make the pairs look like different things too. We can build off whatever we want. So, yeah, there you go. All right, last observation. The elements, the order of these elements doesn't matter. So we can shuffle these however we want. And in fact, we are going to shuffle them. We're going to put a particular element at the end, right? We're going to find some element and put it at the end. And then the first all of these elements, these will all be handled for us. We'll handle these elements by building off some previous element. So we'll take some previous element and then add or subtract this element. And that way, since we know every element except for the last one is going to be the difference between the element in its position and one of the elements before it. Okay? All we have to do now is find some way of adding and subtracting that starts from 0 and ends up at 10. Now you might be asking, David, why do we start at 0? Well, we're subtracting two things at every position in the array. So if you add 12 to every element in the array, you'll subtract out that 12 later. So you might as well have the first element be 0. Like it doesn't help you to add a constant to every number in the array. So you might as well just leave the first element at 0, so it's simple. Okay, so yeah, so like I mentioned, what we're going to do is we're going to see if we can reach 10 by like adding or subtracting certain numbers in the array. So in this case, you can't really do it, I don't think. Can you? Yes, you can. You can do 0, and then you can do the 4, and then the 5, and then the 1. And this makes 10. So if we do the cumulative sum of this, you have 0 plus 4 is 4, plus 5 is 9, plus this is 10. And then we have the 7. So we have a 7 here. We can just build the 7 off the 0. How about that? Or so this is 7. So in this case, we have these links here. So we know the elements 4, 5, 1, and 7 are all satisfied, obviously, because, and these are also all positive, but they could be negative, right? We could make this -7, and that would work too. We would just change the order of the direction. But since we've made this 10, that means we've satisfied the array. So yeah, that's the idea. We want to see if we can satisfy any of these numbers. Now, in this case, we satisfied the 10, but we could do an even easier version. Obviously, 5 is just 4 plus 1. So, or let's do a slightly different version. Let's say 1. Let's say we're trying to make 1. You can make 1 by 5 minus 4. So we could have a 0, and then we can have a 5. We can also subtract 4. So then it would be 1. And then we could have, so now we've handled the 5, the 4, and the 1. We want the 7 and the 10 as well. So we put the 7 and the 10 here. So in this case, we can get 4 by doing this. And here we have the 1. So the 1 is satisfied. So what we're trying to do, more formally, is for each element, we can add or subtract it, and we want to make some element in the array using all of the other elements before it. Yeah. You don't actually have to reorder it, because if some element is like the sum of plus or minuses of everything before it, that means including that element you equal 0. So in this case, you have like this 1, 4, and 5. They kind of like form a chain, or they form like a circle. So you can do 1 plus 4 minus 5 is equal to 0. Let's try this again. You can do 1 plus 4 minus 5 is equal to 0, which means if you take any one of these and move it to the other side, right? If you have 4 minus 5, this is equal to -1. So you put one thing on one side, and then it'll be handled by itself. Yeah, I think that's a good enough explanation. So what we want to do, just to recap, is see if we can use a prefix of these numbers to add or subtract up to this number using each element 0 or 1 times, or -1 times, I guess. What does that look like? Well, we can just do store like a Boolean array for all of the things we can reach, and then I offset my stuff by 10 to the 6th. And then for each element in the array, you can, if you can reach this element already, that means this element is one of the things that you can reach with a subset of previous elements, so it's going to be possible to do this. Then, you have to like mark all of the other things that you can use this element to reach. So that's what this does. So you can, if you could reach j before, you could still reach j. You don't have to use this element. Otherwise, you could add this element, or you could subtract this element. Or I guess, sorry, this is really subtracting it. So you could come from j plus this element if you wanted. Or you could come from j minus this element. Yeah, so that's the idea for D. Kind of a long explanation. Sorry if that was unnecessarily long-winded. Okay, colors and intervals. I don't have a proof for this, but I have some intuition that feels very right, and there were no hacks by anyone good on this contest, so I suspect this intuition is correct, but it's not formal. So in this problem, you have n different colors, and then you have k copies of each color, and then they're in a list. So in this case, we have color 2, then color 4, then color 3, 2 copies of color 1, another color 4, another 2, 3, etc. You get the point. And then what we have to do is create, like we have to pair up some 2's. So maybe we pair up these 2 2's here, for instance. In this case, we will cover these 3 elements in like one range. And what we want to happen is we want no element covered by more than n divided by k minus 1 ceilinged intervals. So yeah, that's the idea. How do you do it? Well, I just used a greedy approach. I think it's right, but I might be eating my words on this in a minute. the idea is we can like just do everything, like consider some prefix. If we have a 1 and we can match this 1 with the previous one, we might as well do that. So if you can match it, then make that matching and then increment the number of times everything is used there. And if you can't match the 1 because it's used too many times, then don't match it. So let's look at what this would look like more formally, I guess. So we can use this array here. 2, 4, 3, 1. 4, 2, 3, 2, 1, 3. Four. Okay. So this is what the array looks like. What we'll do is we'll say, okay, here's the last 2 we've seen, here's the last 4 we've seen, here's the last 3 we've seen, here's the last 1 we've seen. Okay, we see a 1. So first of all, before we start, let's say how many times are we allowed to cover something? We have 4 colors, or we have 4 numbers, and we repeat things 3 times. C-linked. So we're allowed to have an overlap of 2 maximum. Okay, so we have, this is our second one, so we can make this pair. So let's make this pair here. We've done it. Okay, so now since we only need to match the ones, oh, I didn't mention this, but you need to match every number. You need to make 1 pair with every number as well. So we've matched the 1s, so now there's no reason for us to use any 1s in the future. So everything in this range we need to increment by 1, and then we delete all of the 1s. Oh, crap. Maybe this doesn't matter? Oh, it does matter. Yeah, it does matter. Okay, good. I thought I had messed up, but I guess I haven't. Yeah. So we're not going to use any future 1s. We're not going to use any future 1s. And these elements, we need to update their counts by 1, because now they're covered by 1 range. And then we also know any range that went this way is not going to break a previous range. So there's not really any sense in not picking this, right? In order to not pick this, like we know all of the elements here are not inherently super useful. So the only reason this range would be bad is if it breaks at least 2 ranges, like for 2 different numbers. And that would have to be like 1 to the left and 1 to the right. It can't break 2 ranges on one side. We also know it's not breaking any ranges to the left. So it's fine to pick. That's my hand wavy proof. Yeah. So we picked this range. Okay, now we see a 4. So we would consider this range. We would pick it because it doesn't make any number picked 3 times. Okay, so now we've incremented these all by 1. Now we see a 2. This is our second 2. The previous 2 is over here, so we consider this range. But that would make this picked 3 times. So we can't pick this 2. But we know our previous 2 now is going to be right here. Okay, we see this 3. Again, we're not allowed to pick this range because it would make this pick 3 times, so we don't pick it. But our previous 3 is here. Now we see this 2, and we can pick this range. So we do. We see this 1. We don't need 1s anymore because we've solved them, so we ignore it. We see a 3. We consider the range to the previous 3, and then we take it, and then we these are all now incremented twice. Cool. And then we see a 4. We don't need the 4 because we've matched our 4s before. So that's the idea. The operations you need for this are a segment tree with range add 1 and then range max. You can do this with lazy propagation, and that's the idea behind the problem. Okay, yeah. So segment tree is pretty straightforward. I guess I'll just stop here. You can pause if you'd like. But yeah, pretty classic segment tree. And then in the main method, we have this array. I keep track of the last time you saw each index and then whether each thing is used. And then I keep track of the answers, which I print at the end. What is this? This is the max thickness allowed. And then, yeah, I just do exactly what I told you in the problem. So if it's used, I skip it. If we haven't seen this thing before, then I mark this as the last thing, and you can't pick the prefix before the first one. Otherwise, we consider taking this range. If we can take it, then we do. Otherwise, we don't. And then we update the last time we've seen this number. So taking a range entails doing a range add, marking this color as being used because you've picked it now. So in the future, you don't want to pick this color anymore. And then adding this to your list of answers, which you print at the end. I don't know how to prove that you can always do it in this many intervals. Maybe I should think more about that. But I don't think, I think this is the minimum answer. So I wouldn't be able to off the cuff tell you what the minimum answer is, but I can kind of believe that this achieves it. Like, it's hard. I don't think it's possible to improve upon my answer in the general case at all. I don't think it's possible to ever get better than this answer. But it's not obvious. Like, a lot of work goes into setting this bound, I think, in the paper. But I can prove that this is equal to the bound in all cases. I just wouldn't be able to tell you that this is what they're looking for. Okay, last one, teleplanting. This one also wasn't really bad at all. So you have these teleporters, and like you have this big line that you want to walk through. Let's draw it like this. So it's position 0, 1, 2, 3, 4, 5, 6, 7, 8. Then you have these teleporters, which look like this maybe. So maybe you have one from 5 to 1. Initially it starts turned off. Then you have one from 6 to 4. Initially it starts turned on. And then you have one from 2 to 3. Initially it starts turned off. So what happens is you walk through this line, and then when you reach a teleprompter, or teleporter, here this one's at 3. So initially it was off. So now what will happen is it will turn on. So now the next time you go through it, you'll be teleported back to 2, if you go through it again. So now we keep walking, we're at 5, so now this one was also turned off, so we'll be able to walk through it this time, but next time we'll get teleported. Okay, and now we'll walk to the 6th one. Uh-oh, we hit the 6, so we get teleported back. So we get teleported back, so now we're back at this 4, and also this gets turned off. So the next time we walk through it, it will be okay to walk through. They alternate, by the way. It's not like turned off forever. So we're walking forward, and then we hit this 5. Now we're at the end of a teleprompter that's turned on, which means, uh-oh, we get thrown back again. So this gets turned off, and now we get moved back to 1. Now we'll walk forward, we get to 3. Same thing happens again. This is turned off, so now we'll be back at 2. And then we walk to 3. When we hit 3, this one gets turned on again, but we don't need to travel back through it. When we hit 5, this gets turned on again, but we don't need to travel back through it. When we hit 6, this one gets turned on, and then we will hit all the way to the end here. So in total, we can track how far we've walked by just the sum of these arrow lengths. That's the problem. How do you solve it? Okay, let's look at this in reverse order. So we'll undo all of these crazy operations. Okay. So what's going to happen is at the end, we're going to walk from 6 to 7. That's going to be the last thing that happens. We're only going to do this once, because we're never going to travel backwards from 7, obviously. So the question is, how many times do we walk from 5 to 6? Well, the first time we walked from 5 to 6, we're going to get teleported backwards. The second time, we'll be able to walk through. So this will happen twice. We also know, since the first time we get teleported backwards, that this backwards teleportation happens once. When we walk, how many times do we walk from 4 to 5? Well, we know we leave 5 twice. So we're going to, the first time we walk to 5, we will be able to walk through. The second time we walk to 5, we're going to get teleported back because this will be turned on. so we don't walk through. The third time we walk to 5, it'll be turned on, or we'll be able to walk through because it'll be off again. So that means we do this part 3 times. It also means, since we had a 0 here, that we get teleported back along this path once. Okay, and we can figure all of this out only looking at the suffix. So from 3 to 4, how many times do we walk from 3 to 4? Well, we know we leave 4 3 times. We also know we get teleported back to 4 once. So 4 has an in degree of 1 plus whatever this is, and then an out degree of 3, which means this needs to be a 2. That easy? It's just kind of like solitaire here. All right, one more time. So we're going from 3 to 4 twice. How many times do we need to walk from 2 to 3? Well, we know the first time we'll make it through. So when we go from 2 to 3, we'll make it through initially. And then when we go from 2 to 3 again, then we don't make it through. We get teleported back. And then we need to leave 3 twice, so we need to go from 2 to 3 one more time. So that means, okay, we get teleported back once, and then we get moved across twice. Okay. From 1 to 2, we need to enter 2 twice. We enter it once from this teleportation, so that means we need to enter it. I've messed up here. This happens 3 times. Yeah, this is 3 times. So we need to enter 2 twice. Happens 3 times because there are 3 rows here. We need to enter 3 times. We enter it once from itself, so this needs to happen. This needs to be a 2. Because 2 plus 1 is 3. Okay. Then we know we leave 1 twice. We enter it once from a teleporter, which means we have to walk into it once. And everything works out. That means we leave the starting point once. So cool. So now we have, for each of these segments, we have how many times they are walked across. And the sum of their distances times the number of times we walk across them is just going to be the answer. And that's it. It's that easy, folks. That easy. So I guess one minor implementation detail here is that another way of calculating this, rather than splitting it up into segments, is you can just say it's going to be the total length. You're going to walk across this thing once. And then every time you teleport backwards, you have to walk backwards across that. So you can just look at, if you know how many times you take each teleporter, you just say however many times you take it times the distance you get teleported, that gets added into your total. And that's what I did in my actual solution. So yeah, it looks like this. So you say, we have all of these events, and then the start events and end events. I make my events, I sort them in reverse order from end to beginning. And then if it's an end event, I do this. So the time taken is either, or the times the edge is taken. If the edge starts on, then the number of times I leave it is equal to the number of times I had to bounce back. The teleporter starts on. If it starts off, the first one is free, so the number of times I take it back is that minus 1. Okay, so the number of times that I'll have gone before this is the number of times I've taken this edge, because each of those will have to walk back, plus the number of times I leave it. So that's what this times is, which is the number of, like, that's these numbers here, the 1 and then the 2 and then the 3 and then it's 2 and then it's 3 and then it's 2 and then it's 1. That's times. And then the number of times the edge is used is obviously the number of times I took it back. I have this for both the start and end event, so they're the same. Okay, then if it's a start, then I subtract out this back edge number, right? So if the out degree is 3, this part in degree is 1, that means this has to be 2. So this is obviously 3 minus 1. Cool. And then, yeah, like I mentioned, I just calculate the total length you walk by looking at the number of times you took each edge back times how big that edge is. So that's what's going on here. Don't forget your mods, everybody, but other than that, it should be a nice, easy problem. Definitely easier than E, at least to prove, I think. Okay, so, uh-oh, am I failing system tests? Oh my goodness. Bro. I got Java'd! Ridiculous. I can guarantee this would pass in C++. Bro. This is in Java 8 too, right? Yeah. That is so annoying. That's upsetting. Yeah, I'm pretty sure this passes in C++. Oh, okay. So this is completely different. Yeah, I guess there's a different solution there too. Okay, and you try, yeah, tourist tries like 3 to the 9, which is another way of doing it. Okay. That's annoying. I'm pretty sure this passes in C++. Anyway, ripperoonie. Darn, I lose IGM then, don't I? Maybe. Maybe, or maybe just barely. Yeah, probably. I think I'm gonna be 1 point away. Ugh, that's obnoxious. That is so upsetting. It's gonna be so close too. Java. Okay. That's enough of me raging about my poor decisions and language choice. Yeah, have a great day. Hope you enjoyed the contest and hope you didn't get hacked for stupid reasons. Alright.